Hello and welcome. This is going to be our lecture video for the vectors and projectiles test review. Let's go ahead and get started with a little bit of true false. So vector quantities have magnitude and direction. That is a very true statement. That's a really good explanation of what a vector quantity is, anything with magnitude and direction. Distance is a vector quantity. That is false. The vector equivalent of distance is displacement. If I run one lap on the track, my distance is a quarter mile, but my displacement is 0 because I'm back where I started. A vector is represented by an arrow drawn in any direction. I'm going to go ahead and say that that is true. We can use arrows to represent vectors, and the direction does matter, but they can go in any direction. Acceleration due to gravity is about 10 meters per second. That is true. We say 9.8, but 10 is pretty darn close. Acceleration is a scalar quantity. That is false. Acceleration is the change in velocity, and velocity being a vector automatically makes acceleration a vector. The direction that you are accelerating is very important. With gravity, it's always pointing down towards the center of the Earth. And so it's not just a scalar quantity, it is a magnitude, 9.8, and a direction, down. All right, moving on to some multiple choice. If a rock is thrown horizontally and at the same time a stone is dropped, so we've got a rock that's launched horizontally that's going to fall like this, and then a rock that falls like this. Well, horizontal and vertical motion is independent, so that horizontal motion doesn't matter at all. So let's look at our options. The rock will hit the ground first, the stone will hit the ground first. Neither object hits the ground. They are in free fall. They hit the ground at the same time. D is correct. They do hit the ground at the same time. All right, which of these is a possible unit of acceleration? So we're looking for something that is a distance divided by 2 time units. Miles per hour, nope, that's a speed. Inches per century, also a speed. Kilometers per hour, also a speed, but meters per second squared, that is acceleration. It's telling us how much the meters per second are changing by every second. Okay. How does the speed of an object change every second is in free fall? So your options by 10 meters per second every second, because that's the acceleration. That sounds pretty good. But let's look at these other ones. The speed doesn't change in free fall. Nope, things accelerate, so their speed is always changing. The speed decreases. No, that doesn't sound right. The time is the same for every object in free fall. I'm not entirely sure what that even means, but A is correct by 10 meters per second every second because that's its acceleration. All right. Number 9, acceleration is defined as the change in velocity divided by the time interval. So change in position, that is velocity. Time it takes to move from one speed to another speed, that's not really how acceleration is defined. Or time it takes to move from one place to another place, that's average speed again. What is the difference between distance and displacement? So we should just automatically key in distance is a scalar, displacement is a vector. So A can't be right. There is a difference. Distance is measured in meters per second. Displacement is just meters. No, that doesn't sound right. Distance is a scalar and displacement is a vector. Yes, that sounds right. Displacement is only for vectors in free fall. No, we can use displacement for any type of movement. All right, an object is dropped and free falls. What is its speed after 3 seconds? So we can use a little kinematic equation here, or we can think about it intuitively. But V final equals V initial plus AT. If it's dropped from rest, then the V initial is going to be 0. The acceleration is about 10. It's really 9.8. And 3 seconds. So V final equals 0 plus 10 times 3. V final equals 30 meters per second. There's only one that's at 30, so we'll pick that one. With the actual 9.8, it would be a little bit less. And let's take a look at some matching. So vectors in opposite direction, if they're pointing in opposite direction, we should probably subtract. So I'm going to guess C for now. A quantity that has magnitude only, that sounds like a scalar, so that's going to be A. The path of a projectile, trajectory, that sounds right. And then the sum of two or more vectors is the resultant. Yep, that sounds right as well. So C, A, B, D. Now on to some short answer. A skydiver jumps out of a plane, ignoring air resistance. How fast is she going after 7 seconds? The kinematic equation we want for this is final velocity equals initial velocity plus a t. Here, let's use the 9.8 meters per second as our acceleration. The time is going to be 7 seconds. Initial velocity is 0, and we don't know the final velocity, but this should solve for it. So all we really have to do is 9.8 times 7 to get 68.6 meters per second. So that's closing in on like 150 miles per hour after just 7 seconds of free fall. How far has the skydiver fallen after 7 seconds? So as we get into more tricky kinematics, it can be useful to write out what we know. We know our initial velocity is 0. We know our time is 7 seconds. We know our acceleration is 9.8. Can we figure out our distance from this information? So this doesn't have V final, so we'll pick the equation that doesn't have V final, and that's distance equals V initial times time plus 1/2 AT squared. But when V initial is 0, this term in the middle cancels out, and we get just distance equals 1/2 times 9.8 times 7 squared. You plug that whole thing into your calculator. And we get 240.1. The distance on that, it's a distance. The unit on that is meters. Okay, calculate the resulting velocity of an airplane that normally flies 385 kilometers per hour if it encounters a 50 kilometer per hour tailwind. We're missing the per hour there, but it's a tailwind. It's got to be kilometers per hour. So we're going 385 through the air, but the air itself is also moving 50 kilometers per hour. And it's a tailwind, so that means it's pushing from the tail of the wind, helping to push that plane along. So we'll just add these together. 385 plus 50 equals 435. So 435 kilometers per hour. And what we would say is that's our ground speed. Ground speed. All right, the same plane in question 2A now encounters a 50 kilometer per hour headwind instead of a tailwind. So it's going 385, but now the wind is pushing it back 50, so we subtract 385 minus 50 equals 335 kilometers per hour. That was 385 right there. And that's our ground speed again. All right, moving on. I launch a projectile with a horizontal velocity of 10 meters per second. I'm just going to draw that right away. Horizontal is going 10 meters per second, and a vertical velocity of 12 meters per second. How fast and what angle does it initially fly? So we'll add these together to come up with our resultant. To figure out how fast, we're just going to do the Pythagorean theorem. We'll label this side A and this side B and this side C, and recognize that this is a right triangle. So A squared plus B squared equals C squared. Now solve for C. 10 squared plus 12 squared is going to be 244. And then we take the square root. This is going to be 15.6. So 15.6 meters per second is our velocity. And what angle? So now I'm going to relabel these not as A and B, but I'll say this is my angle theta, meaning that this is the opposite and this is the adjacent. Tangent of theta equals opposite 12 over adjacent 10. Now I take the inverse tangent of both sides. And I get 50.2 degrees from horizontal. That is our launch velocity. All right, now we have to do some sketching of vectors. Use the following individual vectors to graphically find the resultants. Label the resultants R. The first one we want to do is A plus D. So vector A is going 4 kilometers north, and then D is going west. So if I'm going to go north and then west, I should maybe start somewhere over here. So 4 kilometers north, 1, 2, 3, 4. And then plus D, I'm just going to add this, 5 kilometers west, 1, 2, 3, 4, 5. And then the resultant would be just a diagonal that way. Label the resultant R, so we'll put an R right there. And we could use the Pythagorean theorem to find its length, and we could use tangent to find this angle. All right, number 5, we're going to go B plus C. So we're going to go south and then east. So I'll start somewhere up here. 6 kilometers south, 1, 2, 3, 4, 5, 6. And then 5 kilometers, we're going 2 kilometers east, 1, 2. And then connect them up. That right there is your resultant for B plus. All right, a few more word problems. So given the following situation of a marble rolling horizontally on a table, once the marble rolls off the table, calculate how long it will take to reach the floor. So how long it takes to reach the floor depends only on the height of the table. It has nothing to do with how quickly it's moving horizontally because of the independence of motion. So the distance we need to cover is 1.5 meters. Our initial velocity is 0. The acceleration is 9.8. I'm going to do this with down being positive. That way my distance is also 1.5, and I just need to find the time. So this is the kinematic we need. Distance equals initial velocity times time plus 1/2 at squared. Initial velocity is 0, so that middle term goes away, and I get 1.5 equals 0.5 times 9.8 times t squared. Let's keep working on this. We got 1.5 equals 4.9 times t squared. Divide both sides by 4.9. 1.5 divided by 4.9 is 0.306 equals t squared, and then we'll take the square root of both sides. And we get 0.553 seconds. All right, next up, calculate how far the marble will land from the end of the table. So we're already told that its horizontal velocity is 10 meters per second. If we multiply that by 0.553 seconds, which is how long it has in the air, we'll get its total displacement. Multiply by 10 is easy, just move the decimal point. So this is 5.53 meters before it hits the ground, approximately.